Alrighty, hello and welcome to Office Hours tonight. Oops. Okay, we totally can walk through exercise 6. Let me pull it up. As far as exercise 8 goes, and I might have to adjust the due date on this thing. I don't remember. I think I made it due on the 11th. But I might push it back a little bit. Sorry, Canvas is still loading the internet. There we go. I was about to say something about my internet being a little slower than normal this evening, but I think it's since I was about to call it out in the live stream, and it shaped right the heck up. All right. So, let's see here. Oh, Jason, really? Okay. I will correct that. I'll correct that right now. Let's see. Okay. Let's open there. Let's open assignments. Experiment 10 student data. You are totally right here. All right, Jason, I am so sorry about that. Your name is now on Group 5. All right, let's see. Exercise 8. Let me open up the calendar here. You know, I'm gonna bump exercise 8 back. I'm gonna bump exercise 8 back. Where'd my calendar go? All right, we're gonna push this back to the 16th. And so the reason why I'm moving it back to the 16th, so Kate, to answer your first question, when do I recommend you start exercise 8? Realistically, so we'll cover the material for exercise 8 in lecture, and I was looking at my lecture schedule today to kind of plot things out, and realistically, I believe we'll cover it in lecture on December 9th, and the original due date for exercise 8 was the 11th, so that would put us lecturing on it and then making it due 2 days later. And it's not a very long exercise. There's only 7 problems in it, but they have more calculations to them than it's not the hardest thing, but it's also not like necessarily the fastest problems out there. Plus, it'll be new material, so I'm going to bump that back. So that's when we'll cover it. And I just changed the due date, so now it's due on the 16th. So I would recommend, starting it. I would start it after lecture on the 9th. That's when I'd recommend to start exercise 8, and now it won't be due 2 days later, so it's a little more equitable. Okay, so let me pull up. You had a question about exercise. Wait, that's experiment. There we go. Exercise 6. And it's loading. Yeah, totally. It's material we haven't covered yet. We'll get to it after what's it called? After we finish. Oh my gosh, it's just been a long day. Intermolecular Forces, that thing that we started lecturing on today. We'll finish that on Monday, and then probably start talking about colligative properties is the kind of subject that that falls in under. All right. Sorry, the internet's still pulling up. Exercise 6. Lab exercise 5, I believe. Oops. Eric, at this point, we've covered all of the material on exercise 5 in lecture, so you're totally good to start working on that, dude. All right. Oh, sorry. Right, because I made exercise 5 available, but then I didn't set the stage. Or I didn't set the due date. I'm probably gonna make it due like at the end of the semester. We already have several things due on the 11th, so rather than put it there, I should probably bump it back. I'm gonna put it due when exercise 8 is available on the 16th. Let's see. Just so we don't have everything kind of piled onto the 11th. And I just set that due date now, so if you were looking for it earlier and thought, I didn't see it there, then that's because it wasn't there. I just added it. Okay. Let's see. So, Kate, you want to see a problem that's similar to this one. So it's I believe you said it was number 22. On exercise 6. And I'm just going to essentially just change the numbers here. Whoops. There we go. Kate, you're right. So let's see. So so here, let's read the problem. I don't think it specifies a unit, but let's see. So let's go with 220 kilograms of water cools from 105.0 degrees Celsius to 42.0 degrees Celsius. Oh. Hang on. All right. What is the change in thermal energy for the water if the specific heat of water is 4.184 joules per gram degrees Celsius? All right, so whenever you're asked to find the change in thermal energy, that quantity is Q, right? Q represents the change in thermal energy. And we have an equation there. We know that Q is equal to mass times the specific heat capacity times the change in temperature. And you can see that we have our mass, right? We have our specific heat capacity. It's right here. And even though we're not explicitly given our change in temperature, we are given our initial and our final. Right? So so we have enough to solve this problem. There's one minor thing that we got to watch out for. Here we have kilograms, a mass of water in kilograms, and in the specific heat capacity, the mass unit is grams. So we have to calculate a change in temperature. We have to do a unit conversion, kilograms to grams. But after that, we just plug in our values into this equation, and we'll be good to go. So let's go ahead and start by converting 220 kilograms of water to grams. 1 kilogram is 1,000 grams. So kilograms cancel. And the answer is, my calculator is telling me that my answer is 220,000. And we know that the number of sig figs that we start with, the number of sig figs we have to end with, because we're doing a metric unit conversion, so it doesn't mess with our sig figs. We started with 2, we ended with 2, so we don't have to round or write it in scientific notation or anything. There's our mass in grams. We also need to calculate our change in temperature, which is final minus initial. Now, our final temperature is 42.0 degrees Celsius, initial 105.0 degrees Celsius. And when you punch in 42 minus 105 to your calculator, your answer, the answer that the calculator gives, is negative 63. However, we just did a subtraction. So our precision, the precision of our answer must equal the precision of our least precise number that we subtracted. And both of these numbers are precise to the first decimal place, so we need to add a 0.0 here. 0.0, negative 63.0 degrees C. That is our delta T. All right. Now, with that in mind, we can actually calculate our change in thermal energy, which is equal to our mass times our specific heat capacity times our change in temperature. Plugging these in, we have a mass of 220,000, 000 grams, times our specific heat capacity, 4.184 joules per gram degree Celsius, times our change in temperature, which is negative 63.0 degrees Celsius. You'll notice that grams cancel grams, degrees C cancel degrees C, leaving us with joules, and that's good because we're solving for energy after all. So let's crunch our numbers. We've got 220,000 times 4.184 times negative 63. All right, this number is huge. My calculator is telling me the answer is negative 57,990,240. Now our units are in joules right now. That's the only unit left standing. And our sig figs, let's see, our delta T has 3, our specific heat capacity has 4, but our mass only has 2, so we need to round to 2 sig figs, and this 9 will round up. So our answer in joules, with the correct sig figs, is 58 million joules of energy. And Kate, you're totally right. This problem does not specify whether or not our unit should be in joules or kilojoules. Since this problem states answers in both joules or kilojoules, just to show you what this would translate to, 58 million joules is 58,000 kilojoules. So it just knocks 1,000 off. So that is, this problem obviously has different numbers different values. So, you know, the answer, the sig figs may change, but that's how you work. That's how you work this problem. Um, I'm glad that helped. I all I can say about this one, Kate, is I've double and triple checked it, and there's only one correct answer in there, and that's about all I can say without giving the answer away. Totally. Yeah, so as far as losing energy goes, oh snap! I made a problem. I made a problem. I made a mistake. Yeah, both of these should be negative 58 because they're negative right here because our delta T is negative. Ah. Okay, that is a great question. So and to answer it, um, um, the definition of a formation reaction the definition of a formation reaction is this. It is the formation of 1 mole of a compound from its constituent elements in their standard state. So the answer to your question is the definition of a formation reaction is the formation of 1 mole. So the equation that you need to get is you need to get the equation of whatever that thing is in 1 mole, and then this is the one time this semester where you're allowed to use fractions in a balanced chemical equation, because, for example, if you're forming solid, not gaseous, if you're forming solid iron 3 chloride, well, its constituent elements in their standard state would be solid iron plus Cl2, and so you'd have to use 3 halves. This is the formation reaction of iron 3 chloride. Totally. Yeah. No, dude, no worries. I'm really glad you asked it, actually. I bet you're not the only person with this question. Okay, let me see. Number 3. Here, I've got to actually pull up the packet. The other questions I could answer off the top of my head, but this one, the other ones I got to actually look at. Oops. There we go. Let's see, number 3, review packet. Here we go. Okay, question 3. 15, okay. 15-liter metal cylinder contains 1.08 moles of nitrogen gas, 24 degrees Celsius, and 0.12 atmospheres when the moles. When 1.2 moles of nitrogen gas are added to the cylinder, the temperature increases to, let me see. And then we're asked to find the pressure inside the cylinder. Well, if we wanted to find the pressure, PV equals nRT. Oh! Kate, you could use either the ideal gas law or the combined gas law for this problem. Sorry, I just said for this problem. So for problem 3, you could use either the ideal gas law. So for packet 3, problem 3, you actually have enough information to roll with either. When I wrote this problem, to be totally honest, I was thinking about the combined gas law, but you actually have enough information to use the ideal gas law as well. So either one is totally fine. If I hadn't told you that the volume was 15 liters, then you would have to use the ideal gas law. But because I gave the volume of the cylinder, you're actually totally good to use the ideal. And then number 7, is there a mistake? Let's see. It's possible. Oh my gosh, that's hilarious. Yes, I would say problem 7 just says A100, and that's it. So I'm just going to delete the A100 part, and now there are only 6 problems. I was originally considering putting 7 on, but then I decided on 6. I didn't realize that I had started typing number 7. So yeah, so that's what that is / was, but now it's gone. So there you have it. That one was for real. You're like, A100, no units, no question. What could it mean? It's like a next level problem where you have to make it up and then solve it. That's actually just called being a chemistry professor. All right, let me dial that stuff up. Oh, fun. All right, let's see if we can figure this out. let's see, chapter 10. Starting with number 72. Let's see. Okay. 72. Draw an MO diagram. And predict the, bond order of dilithium cation and dilithium anion. Do you expect these molecules to exist in the gas phase? Okay. So let's start with dilithium cation. Now, we should look at the electron configuration for lithium, which is 1s2, 2s1. All right. Now we're going to do this just like we always do. We draw a y-axis. We have in play a 1s orbital and a 2s orbital on either side, right? Because we're dealing with two lithium ions. Now, we have two electrons in our 1s orbital, and we have one electron in our 2s orbital. Or we would if we were doing dilithium with no charge, right? If we had two lithium atoms with no charges, then we would have 3 electrons on either side. But because we have this positive charge, this means we have one less electron. We have one less electron than we should, so we need to remove one of the electrons from this orbital diagram. So we are going to erase one of our high energy electrons. All right, so we have to delete one electron. We're going to pick from one of the highest energy orbitals. Now, so if we had just dilithium, 2 lithium atoms, we would have had 6 electrons. Now we're down to 5 total electrons. All right, now we need to mix our atomic orbitals together, and lithium only has s orbitals to mix. So we will form a sigma and a sigma star from our 1s orbitals, as well as a sigma and a sigma star from our 2s orbitals. And let's see, we got to draw our dots to show which atomic orbitals mix to form these molecular orbitals. All right, now that we've mixed our orbitals, we need to place our electrons. We're going to place 1, 2, 3, 4 in our 1s sigma, followed by our 1s sigma star. And now with our 2s orbitals, because we're dealing with lithium cation, we only have one electron to place. Right? It goes down to sigma. Now that we've placed all our electrons, we can calculate our bond order. And as always, it's the number of bonding electrons. Right? So we have 1, 2, 3 electrons in bonding orbitals minus our electrons in antibonding orbitals. And here we only have 2 electrons in antibonding orbitals divided by 2. 3 minus 2 is 1. So our bond order is 1/2. All right? There's a bond order of 1/2. That means that we have formed half a bond. All right? That's because we've stabilized just 1 electron. We haven't stabilized 2, but we have stabilized 1. So we would say that dilithium cation will form. That's what they mean by will it form in the gas phase? We'd say yes, it will form because you have a bond order greater than 0. If you have a bond order of 0, it will not form. If you have a bond order greater than 0, it will, because you've net stabilized more electrons than you have destabilized. All right, so that is lithium cation. Let's go ahead and take a look at lithium anion. Oh wait, what am I doing? We're still doing 72. So dilithium anion. Again, the electron configuration for lithium, 1s2, 2s1. Now, we have our 1s and our 2s for our 2 lithium atoms. All right, we know how these are going to mix. Forming sigma and sigma star. And these are all coming from our atomic orbitals. All right, now, normally we would have 2 electrons in our 1s orbital, 1 electron in our 2s orbital. But we have to account for our anion. All right? Because this is dilithium anion, that negative charge tells us that there's 1 extra electron. So we have to add 1 extra electron to one of our 2 lithiums. It doesn't matter which one. Just like we had to take away an electron when it was a cation. All right, now we're going to place our electrons. Our 4 electrons from our 1s orbitals go into their respective sigma and sigma stars. Our 3 electrons in our 2s orbitals, well, the first 2 drop down into sigma, and then the third one pops up into sigma star. We can now calculate our bond order, because it is equal to the number of electrons in bonding orbitals. Here we have 4 electrons in bonding orbitals minus our electrons in antibonding orbitals, and we have 3 electrons in antibonding orbitals divided by 2. Again, we find that 4 minus 3 is 1, so we have a bond order of 1/2. And since, even though it's not a full bond, it is a bond order of 1/2, and so dilithium anion will form. Again, if it was a bond order of 0, it would not form, but even a bond order of 1/2 is enough for a molecule to hang together, if not by the skin of its teeth. All right. Oh, yeah, that was 72. All right, 74. Sketch the bonding, anti-bonding, and anti-bonding. Oh, well, I guess first, before I move on to the next one. Before we barrel on ahead, I should probably check to make sure. Okay, yeah, totally. Yeah, 72 is a cool problem. Okay, awesome. Okay, so now let's check out number 74. All right. Sketch the bonding and anti-bonding molecular orbitals that result from the linear combination of the 2pz atomic orbitals in a homonuclear diatomic molecule. How do these molecular orbitals differ to those obtained from the 2py orbitals? So compare 2py, 2pz. Okay, so this is actually all this problem is asking for, and I didn't use the words, linear combinations, blah, 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 blah. But all it wants to see is, let's see. Okay, good. Basically what it's asking you is to draw the bonding and antibonding combinations when you mix 2pz and 2py orbitals. So for 2pz, when you mix them in their bonding conformation, or I'm going to pick a different color. I'm actually going to skip these over just a little bit. Oops. So when you mix two pz orbitals together to make a bonding orbital, it's when the phasing overlaps. When you mix them to make an anti-bonding orbital, you mix them like this with their phasing. Whoa, that is the ugliest p orbital I've ever drawn. You mix them when their phasing is off. All right, so this is the bonding configuration and anti-bonding configuration for 2pz. Now, when you're mixing 2py orbitals together, in their bonding conformation, you'll recall that py is horizontal, right? It's along the y-axis. So when they bond, it's when you get that direct orbital overlap, matching the with matching phasing on the inside. This is the bonding combination, And then the antibonding arises when you mix opposite phasing together with your two py orbitals. So these are the pictures they want to draw, and when they ask how do these two differ, here this is direct orbital overlap. And then over here we have indirect. Oops. Direct overlap and indirect overlap, creating the pi bond with pz and the sigma bond with py. Ah, yeah, totally. So phasing is a result of the differential equations that describe the probability of finding the electron. And so when you, because that's what orbitals are. They're a calculation for the probability of finding the electron around the nucleus. And for p orbitals, half of the solutions, so the p orbital shape is a cloud of all the possible solutions to that differential equation in 3 dimensions. Half of them have negative signs, have negative values. There's still a place you can find the electron in space. The phasing just represents the fact that half of the solutions to the differential equation that tells you the chances of finding the electron, half of them are negative, half of them are positive. Now, something interesting that comes into play is when you mix your orbitals together, the way these orbitals mix is actually affected by that sign. They either mix with what's called constructive interference, when you overlap regions of the same sign together, you make bonding orbitals. When you overlap regions of opposite sign, it creates destructive interference and you make anti-bonding orbitals. So that is why in the anti-bonding configurations, you're matching shaded with clear regions. Here and here again, shaded matched with clear. And it is why with the bonding, you're matching clear to clear, shaded to shaded, clear to clear as well. These are constructive orbital overlaps for the bonding, and then they're destructive for the anti-bonding. And that's about the best description I can give without actually using multivariable calculus. And so that's where I'm going to halt. If you want to know more, and there's much more, and it's much more complex than I am making it out to be, I'm trying my best to describe it in terms of general chemistry, but if you want to see the full picture, you got to take a little more calculus, and then you've got to take physical chemistry, and which will dive into all of this business. Awesome. Awesome. Okay. My pleasure. All right. Okay, so let's take a look at number 76. Let's see. Okay. So number 76 says, using the molecular orbital energy ordering for second row homonuclear diatomics, in which the pi orbitals lie at a higher energy than the sigma orbitals, draw molecular orbital diagrams and predict the bond order in a molecule or ion with each number of total valence electrons. Will the molecule or ion be diamagnetic or paramagnetic? All right, we did not talk about diamagnetic or paramagnetic when we covered it, so we're not going to do that portion of the problem, but we can totally handle the rest of this. All right, so first, you'll notice that they want us to draw a MO diagram, a molecular orbital diagram. And even before we start looking at the number of electrons they want us to use for our MO diagram, we can actually draw the molecular orbital diagram itself, because it's going to be the same every time. We're going to have our 1s orbital, our 2s orbital, and then our 3 2p orbitals. All right, and we'll have them on both sides of this MO diagram. And before even addressing the electrons, we already know how these orbitals are going to mix. Right? We know that our 1s orbitals will mix to make a sigma and sigma star. We know that our 2s orbitals will also mix to make a sigma and a sigma star. And we know that our 2p orbitals, I'm going to just move them up slightly. Give myself a little more room to breathe. Our 2p orbitals will make a sigma, 2 pi, star, and 1 sigma star. that's ugly. I'm just going to redraw these from scratch. All right. So no matter what we're going to look at, basically the only thing that's going to change is the number of valence electrons that we have to deal with. And you'll notice they also give us a little detail here. They say the number of valence electrons. That means those are the number of electrons in our highest energy shell, which in this case is the second shell. So we also will always have a full 1s subshell that we don't have to worry about. This is going to be full because, again, they tell us the number of valence electrons, and for these molecules, because they said they're second period homonuclear diatomics, that they're going to be, we're going to have this many electrons in our second energy shell. All right, so we're going to start here, and basically it's going to be the same orbital diagram, but just with a different number of electrons in each one. So if we take the first problem, in which we have 10 valence electrons, the thing you got to remember is we are going to be, with these 10 valence electrons, let's see, I'm looking at the problem. In a molecular ion, each with a number of total valence electrons. So this number right here is total. That means that we are dealing with 5 electrons per atom. If we have a total of 10 valence electrons, then that means that we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 valence electrons per atom. All right, and now we have to fill up our molecular orbital diagram and then calculate our bond order. So for our 2s electrons, we're going to place them 2, 4, 6, 8 into our sigma and sigma star. For 2p electrons, we have 6 of them. The first 2 go down into sigma. The remaining 4 will fill pi bonding orbitals. And now we can calculate our bond order. We have 2, 4, 6, 8, 10. 10 electrons in bonding orbitals. In anti-bonding orbitals, we have 2, 4. So 10 minus 4 is 6. 6 over 2 gives us a bond order of 3 for a molecule where we have 10 valence electrons. Let's look at 12. Well, so this is part B. If we have 12 valence electrons, that means that we have 6 per atom. So we're going to go 1, 2 in our 2s orbital. 1, 2, 3, 4, 5, and 6. 3, 4, 5, and 6. Our 2s electrons will fill sigma and sigma star. Now we have 8 2p electrons. We go, the first 2 go into sigma. The next 4 go into pi, and then the last 2 go into pi star. And since those pi star orbitals are equal in energy, those 2 electrons are not paired. They're each in their separate pi star antibonding orbital. Now calculating the bond order here. We take the number of electrons in bonding orbitals, 2, 4, 6, 8, 10, minus antibonding electrons, 2, 4, 6. 10 minus 6 divided by 2 is 4 over 2, so we have a bond order of 2. All right, let's do 13. Hopefully these are kind of falling into a bit of a familiar pattern. Here, 13, this will throw us for a loop. Again, this is total. That means we have 6 in one atom. And 7 in the other. Or we have an uneven number. So that just means that one of our 2 atoms has 1 more electron. 2 go in the S. And then 3, 4, 5, 6. We'll do in the first one, and then the second one we'll get 3, 4, 5, 6, 7. Filling it up now. Our 2s electrons go into sigma and sigma star. Now we have 9 electrons to place. 1, 2, 3, 4, 5, 6, 7, 8, 9. Time to calculate our bond order. Our bond order is, let's see, we have to count our bonding electrons, 2, 4, 6, 8, 10, minus 2, 4, 7. 10 minus 7 is 3. So this is a bond order of 3 halves, or 1 and 1/2. It's the same either way. It's a bond order that's a little stronger than a single bond, but not quite as strong as a double bond. All right, finally, part D. We want to look at 14 valence electrons. All right, again, this is total. That means we put 7 in each atom. So that's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. We fill our first sigma and sigma star with the electrons from our 2s. Next, we have a total of 14 electrons to place. So 2, 4, 6, 8. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, wait, sorry. Hang on. I'm losing count. We have 10 total p electrons. So 1, 2, 3, 4, 5, 6, 7, 8. There we go. 9, 10, right? Because we have 5 electrons in each of our 2p subshells, so 10 p electrons total. All right, so now we can calculate our bond order here. We have in bonding orbitals 2, 4, 6, 8, 10 minus all of the electrons in antibonding orbitals 2, 4, 6, 8. 10 minus 8 divided by 2 gives us a bond order of 1. Awesome. All right, let's take a look at number 80. Okay. Whoa. All right, let's take a look at 80. All right. So according to molecular orbital theory, which molecule has the highest bond order, highest bond energy, shortest bond length? All right, now we kind of focused on bond order in lecture, but one thing that I want to point out is the trend is higher bond order results in a higher bond energy and a shorter bond length. The higher the bond energy, the higher the bond order is, the higher the bond energy is. Those are going to be stronger bonds. One of the interesting things is the stronger the bond is, the shorter it's going to be as well. So we didn't cover that in lecture. We were focusing on bond order, but bond energy and bond length correspond to bond order in this fashion. All right. So let's look at these three molecules. So, actually, where's that thing? There we go. We can actually use this situation. If we look at O2, oxygen's electron configuration is 1s2, 2s2, 2p4. Right? So this tells us how many electrons go in our 1s orbitals, how many go in our 2s orbitals, and how many go in our p orbitals. All right, so goodness gracious, my alarms are just going crazy tonight. So we put our 2s electrons in the sigma and sigma star. Now we have 8 total 2p electrons to place. So we go 2, 4, 6, 8. Calculating the bond order. We have to look at our electrons. Actually, all right. Looking at our bond order. Sorry. Oops. Our electrons in bonding orbitals, we've got 2, 4, 6, 8, 10. Minus our electrons in antibonding orbitals. 2, 4, 6. Divided by 2. This is 4 over 2 for our bond order. So our bond order for oxygen is 2. We have a double bond. Now, check this out. They want us to calculate the bond order for O2 with a negative charge. That means this negative charge means we have 1 electron extra. Right? So that means we have to put an extra electron on one of our 2 oxygen atoms. I'm going to throw it right here. That means that our orbital diagram will be exactly the same, except we'll have 1 more electron in play right here in our pi star orbital. Calculating our bond order here. We count up all of the electrons in bonding orbitals. 2, 4, 6, 8, 10. Minus the electrons in antibonding orbitals. 2, 4, 6, 7. 10 minus 7 is 3. So our bond order here is a bond order of 3 halves, or also correct to write it as a bond order of 1 and 1/2. That's for O2 with a charge of -1. Now, I bet you can guess what's going to happen when we do a charge of -2. This orbital diagram will be the same, except now we have 2 electrons extra. And so we're going to put 1 in each atom. This means we'll have 2 extra electrons in play. And so when we go to calculate our bond order, we have the same number of electrons in bonding orbitals, 2, 4, 6, 8, 10, minus our antibonding electrons, 2, 4, 6, 8. So our bond order here for O2 with a -2 charge is 1. Oh, sure. Let me grab that, or at least the review packet number 3. So, quick question. Oh yeah, totally, totally, totally nuts. Not on exam for either. Oh yeah, totally. All right. So basically, here's what it boils down to. Let's see, and this is whoa. There we go. This is thrown back to chapter 7. All right, so chapter 7, number 55. It says an electron has an uncertainty in its position of, where was that, 55, 552 picometers. What is the uncertainty in its velocity? All right, and the uncertainty principle. So just briefly, the uncertainty principle is that there's a relationship. So you can't know the exact position of an electron and its exact velocity at the same time. You either know exactly 100%, you can know one of them and you know nothing about the other one, or you can 100% know one and know nothing about the other. Or you can know roughly, you can have some uncertainty in the position, and you can know a little something about position and a little something about velocity, but not exactly both. And the equation that relates these, oops, sorry, I didn't mean to close that out. The equation that relates them is this one. The uncertainty wavelength is equal to Planck's constant divided by the mass of the particle times its velocity. So The uncertainty in position is called the de Broglie wavelength. This is uncertainty in position. This is Planck's constant. This down here, this M, is the mass of the particle. And this right here is the uncertainty in velocity. All right. You'll notice that they give us the uncertainty in wavelength. Planck's constant is a constant, and the mass of the particle, they don't explicitly give it to us, but they tell us we're dealing with an electron. So we'll have to look up the mass of an electron. All right. In addition, there's one more twist, and that comes with the units for Planck's constant. Planck's constant has units of joules times seconds. But in order to solve this, we're going to need to right, this is joules times seconds. But to solve this, we actually need to use the proper units for joules. 1 joule is equal to 1 kilogram times square meters over square seconds. So we're going to have to plug this into here for joules. If this problem is going to work out. All right. Additionally, we're going to have to convert. So you'll notice joules has meters, and up here our uncertainty is in picometers, so we'll need to convert those picometers to meters. Let's go ahead and start there. And I'm going to clear this out just because we're going to need more space. So our uncertainty in position is 552 picometers. We need to start by converting this to meters. 1 picometer is 10 to the negative 12th meters. So our uncertainty in position will be 5.52 times 10 to the negative 10 meters. All right. Next, we need to do a little bit of algebra because we need to solve for our velocity. So we are going to multiply both sides by v. So it cancels off of the right side. We then get velocity times wavelength is equal to Planck's constant over the mass of our particle. Next, we divide both sides by wavelength. Dividing by wavelength is the same as multiplying by 1 over lambda. So we get the equation, the uncertainty in velocity is equal to Planck's constant times the mass of the particle times the uncertainty in wavelength. All right, rewriting that equation here. The velocity, uncertainty in velocity is equal to Planck's constant times the mass of the particle times the uncertainty in wavelength. We're ready to plug things in. So Planck's constant is 6.6 26 times 10 to the negative 34th. Now, joules, as we said previously, is kilograms times meter squared over second squared. Times seconds, that's Planck's constant. The mass of an electron here, let me look this up. The mass of an electron in, yeah, there we go. So the mass of an electron in kilograms is 9.109 times 10 to the negative 31st kilograms. And then our uncertainty in position is 5.52 times 10 to the negative 10th meters. All right, now look at what happens to units. First, kilograms cancels kilograms. That's good. The seconds outside here cancel 1 of our 2 seconds, and our meters down here cancel 1 of our 2 meters in the numerator, leaving us with units of meters per second, which is good because that is meters per second is a rate, is the units for a speed or velocity. (6.626) times 10 to the negative 34th divided by 9.109 times 10 to the negative 31st divided by 5.52. All right, so our uncertainty in velocity is 1, let's see, we can keep 366.32 times 10, let's see, times 10 to the 6th meters per second. That is the uncertainty in velocity. Absolutely. Let me hop over to Chapter 9. see, number 9, or chapter 9, number 68. All right, let's see. So let's take a look at what they're asking in this problem. Chapter 9, number 68. All right, so it says for N2O, sorry. In N2O, nitrogen is the central atom. Let's see, 68. Okay, and then it says in OF2, oxygen is the central atom. And then it says, they ask us, to use formal charges to explain why. All right. So let's go ahead and start with N2O. So nitrogen's going to be central. I'm just going to do a quick calculation of our electrons. So we've got 2 nitrogens. Nitrogen has 5 valence electrons each. Oxygen has 6, so we've got a total of 16. To attach oxygen and nitrogen is going to take 2, 4. We've got 12 electrons. That's enough to complete this oxygen's octet and this nitrogen's octet. So we're left with 0. Now, this isn't our final answer because our central nitrogen doesn't have a full octet, but we can get there if we convert if we change some of these lone pairs to double bonds. Now, if you assign formal charges in this molecule, we'd put a positive on nitrogen and a negative on oxygen. Now, the reason why nitrogen is the central, because they want to know why nitrogen is central. Well, if we had an alternate reality, if we put oxygen in the center, we'd have to do all the same things. All the electrons would go in all the same places in order to complete all our octets. The difference is when you calculate formal charges, in this structure, oxygen normally has 6 valence electrons. In this structure, it only has 4, right? 1 per bond. So oxygen would have a formal charge of positive 2. This nitrogen would be neutral, the one over on the left side. But the nitrogen on the right side, nitrogen normally has 5. In the structure, it has 6 in lone pairs plus 1 for the bond. 5 minus 7 is negative 2. So nitrogen is central. The answer here is nitrogen is central because it minimizes formal charge. All right, that's the reason why nitrogen is central in N2O. And what you'll see as we explore OF2 is that oxygen is central in that molecule for the exact same reason. Let's take a closer look at our second molecule. So I'm just going to draw this one out a little on the faster side. So this one, we actually have enough valence electrons to complete every atom's octet without resorting to double bonds. So it's kind of cool. And there are no formal charges on any atom in this molecule. Now you'll notice, if we switch things around, if we put fluorine in the center, we still have enough electrons to complete every atom's octet without resorting to double bonds. But the fluorine in the center now has a formal charge of positive 1, and the oxygen would have a formal charge of negative 1. So again, the reason why oxygen is central, oxygen is central because it minimizes formal charge. So that is the reason for both of these molecules why the central atom ends up being what it is. Oh, sorry. I'm so sorry. Chapter 7. Yes, I can totally do chapter. No, totally no worries. Let me pop over to chapter 7. Oh wait, no, hang on. Okay, let's see. Number 68. But from chapter 7. Oh no, totally no problem, dude. And then you poor thing, like had to like sit through the whole explanation of from something from an unrelated chapter. Okay, let's see. Okay. All right, let's dial this up. So this is chapter 7. Number 68. So let's see. According to the quantum mechanical model for the hydrogen atom, which transition would produce light with the longer wavelength? Okay. So here's... Okay, you're just not sure to tell which is greater or if they're the same. Totally. So here's the deal. When it comes to... let's see where we are. 68. When it comes to... light emission... for hydrogen, light emission for hydrogen boils down to the Rydberg equation, where energy is equal to the Rydberg constant times 1 over the initial orbit squared minus 1 over the final orbit squared. All right, that'll tell you the energy. One thing you'll notice is that all that matters for hydrogen is the orbit. The orbital, P or S, doesn't come into play. All right, so when we look at 68, we have 2 transitions. The first is from n equals 3 to n equals 2. And then the second is n equals 4 to n equals 3. All right. So this is going to be the Rydberg constant times 1 over 3 squared minus 1 over 2 squared. This is going to be the Rydberg constant 1 over 4 squared minus 1 over 3 squared. I'm just going to put a line there because this is going to be RH times 1 over 9 minus 1 over 4. This is going to be equal to RH times 1 over 16 minus 1 over 9. So over here it's going to be RH, and we're going to have 4 30 seconds minus 9 30 seconds, or negative 5 over 32 times RH. And then over here, we're going to have RH times 9 over 6, not 16. 9 times 16 is 144. Whoops. Yeah, totally. Minus 16 over 144. Or this will be negative 7 over 144 RH. And when you compare this guy, 5 seconds, to 7 144ths, this one is definitely larger. So that is the reason why. I totally can. So let's talk about excess reactants. All right, conceptually, right, there are, if you have, generically, a reaction where A reacts with B to produce a product C, all right? One of these two reactants will be your limiting reactant, all right? So we'll just call A the limiting reactant, and B is our excess. Oops, sorry. I meant to change colors. Your excess reactant. If you want to calculate how much excess reactant is left over, you have to take your initial moles of your excess reactant B, then you subtract the moles of B that reacted with A. And when you subtract one from the other, you get the excess moles of B, of your excess reagents. In other words, the leftovers. So, that's conceptually what we have to do. Practically, when you're doing an excess reagent problem, it's also a limiting reactant problem. So you have to figure out what reactant is the limiting reactant, the other one's the excess, and then you do this calculation with it. All right, so this is kind of the conceptual setup, but let's do a brass tacks problem. Let's look at a reaction where we have hydrochloric acid, aqueous hydrochloric acid, reacting with solid aluminum hydroxide to produce water, liquid water, and aluminum chloride, which is aqueous. And now it's a balanced chemical equation, and let's say that we have 1.00 grams of hydrochloric acid and 1.00 grams of aluminum chloride, and we're asked, here's the question, determine the grams of excess reagent or reactants left. All right, so here's, if you're asked to do this, these are the steps that you follow. First, you got to determine your limiting reagents. All right. Once you know your limiting, you know your excess is the other guy. Step 2 is determine. In this case, we're dealing with grams. When I wrote the theoretical example, I said moles. You can also do this with grams. And since we're asked to find grams, we're given grams, it'll be easier to stick with grams. Determine the grams. Looks like theg. Determine the grams of excess that react. Step 3, subtract your number 2 from the initial grams of excess. All right, that is how we're going to solve this problem. Step number 1, let's jump to it. Let's determine which is our limiting reactant. Now, to do that, you could pick either water or aluminum chloride. I'm going to choose water just because it's easier, but you could also use aluminum chloride as the product if you wanted to. And remember, the way you determine the limiting reactant is take the amount of each reactant, calculate the amount of water that could be produced, and it could be either product, but I just picked water. And then once you have that, whichever, excuse me, sorry, I apologize for that yawn. It's been a long day for me, but you pick a reactant, you pick a product, whichever reactant produces less of that product, that is your limiting reactant, and the other one is excess. So let's move through it. So we have 1.00 grams of HCl. First, we have to start by converting grams to moles. HCl has a molecular weight of 36.458 grams of HCl per mole. Next, we convert from moles of HCl to moles of H2O. And we actually don't have to convert to grams of H2O. We can actually stop at moles of H2O because we weren't explicitly asked to get grams, and it'll save us a little bit of time. So grams of HCl cancel, moles of HCl cancel. Let's crunch our numbers. 1 divided by 36.458 times 3 is 0.08, let's see how many, 3 sig figs, 2-3 moles of H2O. All right, this doesn't tell us anything in and of itself. We have to repeat this calculation with our one. Oh wait, I messed this up. The mole to mole ratio is 3 to 3, right? It's a 1 to 1 mole ratio. So here, hang on. 1 divided by 36.458. Okay, sorry, this is 0.0274. So this is 1 gram of aluminum hydroxide. We need to convert from grams to moles. Plus, let's see, where's aluminum? 26.98. Wait, I botched that, sorry. .98. Alright, so this is 78.004 grams per mole. All right. Now we can convert from moles of aluminum hydroxide to moles of water. And this is a 1 to 3 mole ratio. Oh, moles of aluminum cancel. Whoops. Grams of aluminum cancel. Now we go 1 divided by 78.004 times 3. So this would come out to be 0.0385 moles of H2O. So this tells us two things. First, that HCl is the limiting reagent. That means that aluminum hydroxide is our excess reagent, all right? And that is the critical thing. Because if you go back and you look at our objectives, determining the limiting reactant also gives us the excess reagent. Now we know that that excess reagent is aluminum hydroxide, and we can move to the next step, which is determine the grams of excess reagent that react. To do that, so keeping that in mind, to figure out the grams of excess reagent, we actually have to start with the mass of limiting reagent and convert it to grams of excess reagent, because that'll tell us how much excess reagent reacts with this 1 gram of HCl. So we got to convert grams of HCl to moles. Next, we convert moles of HCl to moles of aluminum hydroxide. And this is a 3-to-1 ratio. Last step, we convert, let's see, I gotta recrunch those numbers. We convert moles of aluminum hydroxide to grams. And this is 78.004 grams per mole. Now, grams of HCl cancel, moles of HCl cancel, moles of aluminum hydroxide cancel. So we're ready to crunch our numbers here. 1 divided by 36.358 divided by 3 times 78.004. So this comes out to be 0.715 grams of aluminum hydroxide. And this is important, are consumed. All right, that is our mass that is consumed. So when you look back at our objectives, now we know 0.715 grams of excess react. Now we're ready to subtract this value from our initial value, and we'll be able to solve this problem. So our initial mass was 1.00 grams minus 0.715 grams. You do this math, 1 minus 0.715. My calculator's telling me that the answer is 0.285. However, 1.00 is only precise to the second decimal place. Therefore, we've got to round up. So 0.28, sorry, round up, 0.29 grams of aluminum hydroxide, excuse me, remain unreacted. All right, and that is how you handle a limiting reagent calculation, or sorry, an excess reagent calculation. You determine your excess reagent, use your limiting reagent to calculate how many grams or moles react, and then from your initial quantity, subtract the amount that reacts, and that'll give you your excess reagent, the amount that's left unreacted. Hi, Leanna. I absolutely can do Chapter 11, number 55. Let me just pull it up and see what it is. Oh, wait. Hang on. Chapter 11. All right, let's see. It was number 55. There we go. Okay. In each pair of compounds, pick one with the highest boiling point. Explain your reasoning. Okay. So let's set this up. So chapter 11. Number 55. Okay. So we want to select the compound with the highest, what was it? It was boiling point, right? Yeah. All right. So before we dive in, let's just really quick kind of do a quick overview of what the strategy is on this problem. All right. Whenever you are dealt a problem that's asking you to compare, predict, rank according to highest boiling point, it's really a problem about intermolecular forces. The molecule with the strongest intermolecular forces will have the highest boiling point. All right, so whenever you're given a problem that's asking you to rank them or pick the one with the highest, it's really just code for, can you identify which molecule will have stronger intermolecular forces? All right, and here's how they rank. All right, here's how it goes down. As far as intermolecular forces, from strong to weak. The strongest type of intermolecular force is hydrogen bonding. Followed by dipole-dipole. And then the weakest is London dispersion, sometimes called van der Waals forces or dispersion forces. All right. So if there's one with hydrogen bonding, that one will take the cake. Dipole-dipole beats London dispersion. London dispersion beats, well, only other London dispersion molecules. With that quick kind of overview, let's take a look at the ones they want us to compare. Starting with 55. Oops. 55A. All right, so 55A, it's CH3OH versus CH3SH. Now, you won't really be able to do these unless you draw out the Lewis structure. So that's what I'm going to do here. CH3OH is methanol. This is its Lewis structure. And CH3SH actually has a very similar Lewis structure. It just has a sulfur in place of oxygen. All right. Now, when we compare these two structures together, the thing to remember is everything has London dispersion forces, right? So we know that they all have London dispersion. But actually, before we go down that road, you always want to look for the strongest intermolecular forces first. I'm so sorry. Sorry about that yawn. It's been a long day. So the first question is you want to ask, can either of these hydrogen bond? All right. And there are, you'll recall, two criteria that you have to meet for hydrogen bonding. In order to be able to hydrogen bond, first, you need a lone pair in the molecule. And you'll notice that both of them actually meet this criteria. Methanol has a lone pair. Methane thiol has a lone pair. Sorry, it took me a while to remember what that thing's name was. So they actually both have a lone pair. There's a second condition. The second condition for hydrogen bonding is you need to have, the molecule must have a hydrogen must be directly bonded to a nitrogen, oxygen, or fluorine. And this is the one where I see students making mistakes on quite often. Often they'll think lone pair and hydrogen, but it's not enough to just have a hydrogen. It's also not enough just to have a nitrogen, oxygen, or a fluorine. You must have a hydrogen that is directly bonded to nitrogen, oxygen, or fluorine. And so methanol meets the second requirement, but methane thiol does not. There's no H on a nitrogen, oxygen, or fluorine. So methanol has hydrogen bonding. Methane thiol has no hydrogen bonding. That means that methanol has stronger intermolecular forces, IMF, which means that it has a higher boiling point. All right. Leanna. I'm totally going to do part B and part C. But I want to know before moving on, does this make sense so far? And again, I'm totally going to do part B and part C, but I just want to know how you're tracking, if you have any questions up to this point before we dive into the next part. Okay. Awesome. Okay, and you'll see that as we carry over into part B, there's going to be a very similar line of logic, and then part C has its own unique kind of twist to it. It's still related, but it's kind of its own flavor. So let's go ahead and look at part B, where we are comparing. Let's see where it is. Where is it? Okay, we're comparing dimethyl ether with ethanol. All right, now, when you look at, so again, I'm going to do the exact same thing. I'm going to draw the Lewis structure. And then we do the same over here. All right. So here are our two Lewis structures. And again, I recommend going for the jugular, seeing if you can spot hydrogen bonding, because a hydrogen bonder will have stronger intermolecular forces than a non-hydrogen bonder. And that will make your decision quick, right? So again, with hydrogen bonding, when we look at hydrogen bonding, step number one, we ask, is there a lone pair? And the answer for both of these is yes and yes. We've got lone pairs up in both molecules. Step number two, do you have an H attached directly to nitrogen, oxygen, or fluorine? And that's only the case for one of these two. Whoops, where's my, there we go. That is only the case for ethanol. Even though they both have oxygens and hydrogens, in dimethyl ether, all the H's are on carbons, and so there's no opportunity for a hydrogen bond to develop. So because ethanol has hydrogen bonding, and dimethyl ether has no hydrogen bonding, that means that ethanol, oops, let me space that out a little better. Ethanol has stronger intermolecular forces, which subsequently means a higher boiling point. All right, so very similar to what we saw in part A. We had a hydrogen bonder and a non-hydrogen bonder. The hydrogen bonder has stronger intermolecular forces and a higher boiling point. Now, we're going to use the same line of logic with part C. That line of logic is whoever has stronger intermolecular forces will have a higher boiling point. But as you'll see, determining which one has stronger intermolecular forces will kind of rest on a very subtle detail that I find is easy to forget for most students. All right, so here we're doing methane versus ethane. Again, with all of these problems, I think it's a good idea to just start by drawing out the Lewis structure, because what we're doing is we're assessing the structure of the molecule to determine what types of intermolecular forces are operative. So that's just how I start every single one of these problems. All right. Now, the first thing that you'll notice, and again, I always start with the strongest intermolecular forces because those can be really good, give you an instant front runner. Both of them fail in step number 1. Oops. Are there any lone pairs? Nope. There are no lone pairs on either molecule. So hydrogen bonding isn't happening. All right. Next, what about dipole? Dipole-dipole forces. Well, to have a polar molecule, you need polar bonds, and to assess whether or not you have a polar bond, you have to look at the difference in electronegativity. Carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. So the difference in electronegativity is 2.5 minus 2.1. So this difference in electronegativity is 0.4, which means that all of our bonds here are non-polar. All our bonds are non-polar, so there's no hydrogen bonding, there's no dipole. That means that the only intermolecular force operative is London dispersion, also known as van der Waals forces, also known as dispersion forces. I'm not sure which one Mac's using, but those are all different names for the same thing. I always call them London dispersion forces. But none of these are wrong. So this looks like an apparent tie, right? Neither molecule has a stronger intermolecular force active. So in this case, where you both have London dispersion forces, how do we break a tie? How do we pick one with a higher boiling point? And when you're looking at London dispersion forces, the tiebreaker, all right, when you're looking at London dispersion, the tiebreaker goes to the larger molecule. The reason for that is when we're talking about London dispersion, we're talking about the electrons are buzzing around their orbitals, right? And sometimes they'll both be on the same side of the orbital and create a temporary partial charge, an uneven distribution of electrons in the cloud, in the orbital. And the more orbitals you have and the larger those orbitals are, the more opportunity you get for those London dispersion interactions to build up. So the larger the molecule, a larger molecule will have stronger London dispersion forces. Now, normally this doesn't matter because London dispersion, even the strongest London dispersion forces, are weaker than the weakest dipole. All right, dipole will always beat London dispersion, just like hydrogen bonding always beats dipole. But when you have two molecules that only have London dispersion, the larger one will have stronger London dispersion forces, and that one will have the higher boiling point. So since we both have London dispersion forces going on, we pick ethanol, the larger molecule, to have the higher boiling point based on its stronger London dispersions. Ah. Oh my gosh, yes. Ah. Um. Leanna, I totally don't have a policy like that. But I can't speak for Professor Mahoney. He might totally drop an exam or replace it or something like that. But that's not something that that I normally roll with. But because if I remember right, I think you're over in his lecture, so he's the one with final say on all that sort of thing. Alrighty, and it is now 10, which is closing time for office hours. Thank you everybody for coming out. It was good. We basically had activity kind of the whole stream through. It was a totally solid evening of Q&A. So thank you all. I hope you have a great night, a great weekend, and I'll catch you all on Monday. Later.